So now we are learning about the Samaradis regularity lemma. So let's record the statement. For any epsilon, epsilon is the error parameter that we chose, that later we want to obtain some information about the graph G with up to some error term. And this kind of indicates the amount of error that we can tolerate. Anyway, and when epsilon is given and we also choose this t, small t, then there is this large t only depending on epsilon and t, which satisfies the following. So any graph G, it can contain n vertices, and this n could be much bigger than any this t or 1 over epsilon or t, small t. So no matter what graph we have, you can always partition it into into R parts, which is at most this capital T. So you can partition the vertex set into bounded many parts, and at least small t and most t, so that it's equitable partition. So this is called equitable partition. If each part has the almost same size, as close as possible. So all the sides has the either same size or difference by 1. And most of the pairs are epsilon regular. So Vi, Vj is epsilon regular for all but epsilon times r square pairs. So there are some I, j which yields that this is not epsilon regular, but if you count those pairs, it's at most epsilon r square. Or sometimes you can replace this R3 with this R prime 3, which is a stronger condition. That for each I, the number of pairs Vi and Vj, so I is fixed and J is something we varies. This is always epsilon regular, except at most epsilon R choices of J. So for most of the choices of J, it is epsilon regular. So as I mentioned before, we can consider this weaker version of Samaradis regularity lemma, which says that we don't care about this R1, R2, R3. We just care that we just obtain an epsilon regular partition with at most this many parts. So actually we can use this Samaradis regularity lemma to actually prove this seemingly stronger version of the regularity lemma. So whenever we say Samaradis regularity lemma, we will think of this lemma. And later, we will prove this lemma, this version of the theorem. And I will leave you to actually prove this from this version. And once we have this partition, so let's say we have this partition V1 to VR. This is epsilon regular partition. We can even assume, equitable. Then we can consider R is the graph on vertex set bracket R. So 1 to R consists of the vertices of R, such that it has an Hij inside of ER if and only if this Vi and Vj is an epsilon delta plus regular pair. Or let's write it this way. It's an epsilon regular and the density of between this Vi and Vj is at least delta. So meaning that if you have a V1, V2, V3, V4, V5, and we have these edges between. Some of them are epsilon regular, some of them are not. Then we shrink into 1, 2, 3, 4, 5 vertices. And if this is not epsilon regular, then we don't add an edge. So we can consider complete graph here, and then we delete the edge. So we delete this if this pair is not epsilon regular, and we delete this if this pair is not epsilon regular. We do that, and we also delete the pairs which are sparse. So if between V2 and V3, the density here is smaller than delta is some number, then we delete, and we delete, and then remaining graph is this epsilon. This graph R. So delta is some number that we will choose, and we call this R the epsilon delta reduced graph of the given partition. So graph G is given, and then vertex partition of this G is also given. Then we can consider this reduced graph. Then we can, this R also carries some information about the original graph. So for example, let R be an epsilon delta reduced graph. For a given partition satisfying the above, say R1 to R2 and R3. These three conditions. Then, we can actually show that let's say this dr is the average degree, and dg is d denotes the average degree. Then we can actually prove that average degree of R can be lower bounded by the from the average degree of G. So here later we choose this epsilon and delta, and then from this epsilon and delta we apply regularity lemma, so R is large. So these terms we can actually make sure that this epsilon and delta are not too large. So this constitutes a term which is small. So this roughly we can interpret it in a way that if G has we have a lower bound on the average degree of G, then that kind of inherits into this R. We also have a lower bound on the average degree of on R. So this is also not difficult to prove. So you can, do it by yourself as an exercise. And before actually using this regularity lemma to prove certain, graph problems about finding subgraph. So let's prove some lemma. So basically, how we are going to do is we use this regularity lemma to find certain subgraph inside of another graph G. We want to find the graph H inside of G. or later we want to even count the number of number of subgraphs of G which is isomorphic to H. So that's our goal. And then before doing that, let's prove one lemma. So we say that if this is epsilon regular, that means that there are some uniformity. So even if we take this set, the density between them is, as expected. And even if we take other set, we also have the, similar density. So, we have certain regularity or uniformity there. And we can even prove that a bit stronger uniformity. So meaning that almost all graph in G has almost correct degrees towards a certain set. So let's see what it means. Let's say you have an epsilon regular pair in graph G, and B prime is a subset of P, which is not too small. Then we consider the vertices in A. So we have this A and B. And we pick the B prime. And then now we want to consider the vertices here, and then see how many edges does it send to this B prime. There could be that there are some vertex which, sends edges to here, and then we could deliberately choose this B prime to avoid all these neighbors. Then there could be a vertex which sends no neighbor here, or there could be a vertex which sends lots of neighbor here. Because we could, before taking B prime, we can decide to avoid this and then include certain vertices. So from the first glance, we cannot really control the degree from this vertex to here or this vertex to here. It could be very large or very little. But we can still say that most of the vertices in A has a correct degree towards this B prime. Whatever this B prime is, the set is. So we consider the vertex A, and then we count the number of neighbors of A inside of this B prime. And if this is not as expected, so here again we write that A was for three numbers, say x, y, g. X is not y plus minus g, meaning that either x is smaller than y minus g or x is bigger than y plus g. We say x equal y plus minus g, meaning that the x is between y minus g and y plus g, right? So that was our definition. So we count the number of vertices in A which has long degree. The number of neighbors in B prime is not as expected. Then the number of such set is small. So most of the vertices in A has the correct degree inside of B prime. Yeah. So let's prove this. So we take all the vertices in A who has two small number of neighbors in B prime, and we count the vertices which has too many neighbors in B prime. And then we want to claim that each set has size at most epsilon times size of A. Then these two together is exactly this set. So we are done if each of them has size, strictly smaller than epsilon times A. So assume otherwise. If this A minus has size at least epsilon times A, then what happens? Then you consider the density between A minus and B prime. Then you count the number of vertices, number of edges. And number of edges is that in the bipartite graph, it's a degree sum. You take all the vertices in A minus, and you count the number of edges between the vertex and B prime. And then you divide it by size of A minus and size of B prime. Then the upper part is by definition, you add t minus epsilon times B prime for each part, and you get this. So this is the sum of this many terms. So you can compute this, and this is smaller than t minus epsilon. So the density between A prime and A minus and B prime is strictly smaller than t minus epsilon. And B prime is a set with size at least epsilon times B. And A minus is again, by our definition, by our assumption, has a size at least epsilon times A. But what is the definition of the epsilon regularity here? Whenever you take A prime and B prime with size at least epsilon times A and epsilon times B, the density between them is between t minus epsilon and t plus epsilon. So this is a contradiction to the definition of epsilon regularity. So this implies that A minus has size at most epsilon times A, no, strictly smaller than epsilon times A. And by the same logic, we can show that A plus also has size at most epsilon times A. So this proves the lemma. And now we are actually ready to show that why this concept of regularity is useful to find the subgraph inside of given graph G. Before that, we say that the map phi, which sends the vertices of H into vertices of G, is an embedding if it is injective and for any HUB, which is an H in H, its image is also mapped to an H. Then we say this is an embedding. Then proving that the G has a subgraph H is same as there exists an embedding. So now let's prove this embedding lemma. Let delta and n be some integers, and d is a number bigger than 0. And epsilon is a number bigger than 0, which is sufficiently smaller than the previously chosen numbers except n. So delta and d is sufficiently smaller than delta and d so that this relation holds. And suppose that the vertex set of G has a partition with, say, each vi has n vertices. for all I, and say this Bi and Bj is epsilon t plus regular for all I and j. So we have a partition, then we assume that all of them are epsilon t regular. And let H be an R-partite graph with partition x1 to xr with maximum degree of H and most delta, and each of xi has size smaller than epsilon n for each I. Then we want to claim that there exists an embedding phi of H into G such that all the vertices in Xi is mapped to the vertices in Vi. So in the next video we will prove this embedding lemma.